So a spectrophotometer essentially emits all wavelengths of light, and it has a detector in order to measure that amount of light. So we have two different units that we use for the spectrophotometer. One is called transmittance and one is called absorbance. So transmittance has to do with the intensity of light after it's been placed in the spectrophotometer, and then the intensity of light before the sample. So it's I over I, beginning or initial. So the transmittance is always going to be looking at the amount of light that is passed through a sample. And that's going to be, again, pretty standard on all of the spectrophotometers that you see. While absorbance is going to be the negative log of the intensity over the initial intensity. So it's the amount of light absorbed by the sample. So for this particular lab, we're going to be focused on absorbance. We're going to be focusing on absorbance because what we're leading up to is something called Beer's law, And Beer's law has to do with the relationship between what we call the absorbance of the sample versus concentration. So if you take a XY graph and we put concentration on the X and absorbance on the Y, and it's interesting, absorbance does not have a unit of it. So sometimes you see it A or ABS. So the relationship between absorbance and concentration, the higher the concentration, the more light will be absorbed, which only makes sense. So if we think of a blue sample or something like that, the darker the blue it's going to be, the more it's going to absorb. So if I have my points that I'm going to graph when I create what we call my standard curve, it is going to be what we call a linear fit. So Beer's law is always a direct relationship. So this is a direct relationship between absorbance and concentration. So as concentration increases, so does absorbance. So if we were to take absorbance, we could take it and look at a particular relationship here. So if I took absorbance is equal to epsilon times concentration. So epsilon is called the molar extinction coefficient. In reality, it's just the slope of this line that I create. C is going to be concentration, and concentration is going to be in molarity. And then the absorbance of the sample. So what we do with Beer's law is we take a sample and we take standard concentrations and we read their absorbances and we know what their concentration is. So we get what we call a standard curve or a calibration curve. And so once we have a slope of that line, if I know the absorbance, if I know the absorbance of the sample and I know what the slope is, I could then find the concentration. So I could always take absorbance and divide it by the slope to find the concentration of an unknown sample. So how we're going to use this is in a reaction between something called crystal violet and sodium hydroxide. When you mix these two together, you get what we call a colorless product. So the crystal violet itself is a purple color, but once you add the sodium hydroxide to it, that purple color starts to diminish. It starts to get lighter and lighter and lighter. So what we're going to use the spectrophotometer for is to find the rate of this reaction. So how quickly does it disappear as I add OH? So on the first day of the experiment, it's called the calibration curve day. And what you're going to be given is crystal violet dye, and you're going to make up a series of dilutions. So the stock solution is 8 times 10 to the negative fifth. That's the concentration I'm going to give you for the stock solution. And you're going to do 5 different dilutions. So you're going to put 10 mils into a 100 mil volumetric flask, 8, 6, 4, and 2. So you're going to have 5 separate dilutions that you're going to make up. And you're going to read all of these samples on the spectrophotometer at a value of about 590 nanometers. So you're going to be able to calculate the concentration of the dye from how much you put in there. So you're going to use M1V1 is equal to M2V2 to figure out what the concentration of the dye is. You only put 10 mils in there. The rest of it is going to be water. And then you're going to read the absorbance off of the spectrophotometer. So we are going to be working in different groups to make the dilution. So we're not going to have everybody make up the dilution. And you're going to have a partnership per one spectrophotometer. So you're going to get your own set of data off your spectrophotometer. And just like any piece of equipment, that's going to be the one that you're going to use. And you're then going to get a calibration curve from that. So you're going to need to find the slope of that line because you're going to use that epsilon, that slope of that line, to do the next day's data.